Okay, good afternoon. Can you hear me? Yeah, I've muted you all, so maybe I can't hear you people, but you should be able to hear me. Otherwise, make a comment in the chat box. So let's start today's session. I'm sorry that, last time we had this internet problem, so we had to interrupt the lecture after 1 hour. So I'll have to pick up from where I was from what I was discussing, and I had more or less shown that if I have a P field K, right? For us, a P field is a field which is complete for a discrete valuation with finite residue field, right? Then we had shown this bijection. What is it a bijection between? On the one hand, you have pairs consisting of a finite extension, totally ramified extension of degree D. That D could be anything, any integer D. And the second component of the pair is a uniformizer of L. So look at all such pairs consisting of a totally ramified extension of degree D and a uniformizer of that extension. We had shown that this set of pairs is in bijection with a set of all Eisenstein polynomials of degree D. And what is the bijection? If you have this uniformizer, you take its minimal polynomial, and we had showed that this minimal polynomial is an Eisenstein polynomial. Conversely, if we are given an Eisenstein polynomial of degree D, then we just adjoin a root of that polynomial, and we get not only a totally ramified extension of degree D, but that root is a uniformizer of that extension. So you get a bijection between the set of all such pairs consisting of a totally ramified extension of degree D and a uniformizer of that extension with the set of Eisenstein polynomials of degree D with coefficients in your base field K, right? But when this degree is prime to P, let me call it E in this case, when I'm looking at totally ramified extensions of degree E prime to P, this is in bijection with the set of units of K modulo Eth powers. And the bijection is not canonical in the sense that you have to choose a uniformizer. So when you choose a uniformizer pi, then some unit, this U bar, goes to K adjoin Eth root of U times pi. Pi is fixed, and U bar is in OK star modulo OK star to the Eth power, and to such a unit U, you adjoin this extension obtained by extracting an Eth root of the uniformizer U times pi. Pi is fixed. That gives you this bijection here. Okay, so another way of expressing this bijection is the following. So we have our P field K and an integer which is prime to P, right? And I'm looking at the set of all totally ramified extensions of degree E. Okay, this is the set of all such L is what I want to parameterize. And this parameterization says that they are the same, they are isomorphic. You see here, when I gave a bijection it depended upon the choice of a uniformizer. So if you really want something which is canonical, then meaning independent of the choice of a uniformizer, this is the formulation. Take all the set of all totally ramified extensions of degree E, and on the other hand, take the set of all sections of this short exact sequence. Where does this short exact sequence come from? You see, K star, of course, so K star to Vk is the valuation, and that gives me this map from K star modulo Eth powers to Z mod Ez. So that explains the map Vk bar. What is this? Maybe this should be called omega or something, because omega is what? It's a map from K star, or in fact Kk, the residue field, right? Is the residue field of K to K. It's a multiplicative map, right? The Teichmüller representative. So when I go modulo Eth powers here and here, I get a map which I continue to call omega from Kk star modulo Kk star to the power E to K star modulo K star to the power E. And of course, this sequence can be easily seen to be exact. And this sequence has some sections. That is also easy to see. I mean, basically, you just take the image of some uniformizer here, and this map has a section 1 goes to pi. Any choice of a uniformizer will give me a section, and this section will give me a section here, right? So it has lots of sections, and the assertion, the proposition, or the corollary is that the set of totally ramified extensions of degree E is in natural bijection with a set of all sections of this short exact sequence, right? This is nothing more than a translation of what we have done here. Okay, so now if we fix, how many sections are there? How many sections? Because that gives you the number of totally ramified extensions of degree E, of given degree E, which is prime to P. So the answer is that if we fix one section S, then the others are U times S, where U is a unit, and it's a unit modulo Eth powers. So basically, you just need to find out what is the cardinality of this, which is the same as this. Because U1, the kernel, 1 units, these ones, this is ZP module, and E is invertible in ZP. Therefore, this U1 is equal to U1 to the power P, and this is what implies that OK star modulo OK star to the power E is really the same as KK star modulo KK star K star to the power E. Okay, so we just need to find out what is this? This group here is cyclic of order QK minus 1. So when you go modulo Eth powers, what you are going to get is a group which is cyclic of order, whatever the GCD of QK minus 1 and E is. QK is the cardinality of KK, and minus 1 because you are looking at KK star, then you are taking the GCD with E because you are looking at KK star modulo Eth powers. So basically, the set of sections is in bijection. Okay, slightly fancy way of saying this, slightly fancy way of saying it, is that it corresponds to the H1 of this group with coefficients in this, but the action is trivial. So the H1 is the same as the HOM, and obviously this has exponent dividing E, so the homomorphisms from this are just the same as the elements of this. So, and the order of this group, as I said, is equal to this, right? So that tells you how many totally ramified extensions of degree E the field K has. Okay. Now, suppose you have such an extension and it's going to be of the form K, K adjoin EF root of pi for some uniformizer pi of K, right? By assumption E is prime to P. And the next thing we want to understand is what is the group of automorphisms, or rather K automorphisms of this field L. So you have a map from the set of this, from this group, actually a homomorphism from this group OT KL to the group K star E. K star, you know, is the multiplicative group of the field K, and this little e here in this subscript on the left means that you're looking at the E torsion, or elements of order dividing E. So that thing is, of course, a group of order QK minus 1, GCD of QK minus 1 and E, right? Yeah, because that's, you write K star as, what is it? It's Z times KK star times U1, and the E torsion is really the same. This is not going to contribute, this is not going to contribute, only the E torsion of this will contribute, and that has order this, right? So what is the map from this group OT KL to the E torsion of K star? It takes an automorphism sigma to sigma of this EF root of pi divided by the EF root of pi. It's a bit, reminds you of the Kummer theory kind of map. So the assertion here is that it's an isomorphism of groups. Okay, and that's not very difficult to see because any automorphism sigma will take this to one of its conjugates, one of its K conjugates, and the K conjugates are precisely Xi times itself, where Xi is an element of order dividing E in K star. So you get this bijection. Okay. I mean, in some sense, we have, in order to get this defined, write down this homomorphism, this one here, we have used a pi whose EF root we need to adjoin. Suppose I adjoin the EF root of some other pi prime, and suppose K pi prime is also equal to or isomorphic to K pi. Then I'll get an isomorphism from this choice of uniformizer and from this choice of uniformizer. Are they the same? And the answer is yes, because if it's also obtained by adjoining the EF root of some pi prime, then this pi prime will have to be E epsilon to the power E times pi for some unit epsilon. And then what you have to check is that sigma is taken to the same element of order dividing E. So under pi prime, it's taken to this element. Under pi, it's taken to this element. And these two are the same because you have this sequence of equalities, right? Pi prime is by definition epsilon to the power E times pi. So this epsilon comes out. And here also there's an epsilon because pi, right? But these two cancel and therefore you get the same thing. So this is not very deep. Now we can ask the question, okay, we have parameterized all totally ramified extensions of degree E, where E is prime to P and K is a P field. All totally ramified extensions of degree, totally tamely ramified extensions of our P field K. We have classified them. We have parameterized them. Is it, can we say which ones of those are Galois over K? They are totally ramified. So yeah, that's fine. Then it's fine. Yes. So the answer is that such a totally ramified, totally tamely ramified extension of degree E is Galois over K if and only if this QK minus 1 is divisible by E. E divides QK minus 1. And that's what this one says, right? And why is that? Okay, that should not be very difficult to see from our previous proposition, because this determines, okay, let me just write it here. Or the proof is given here. Okay, so the proposition says further that if it is Galois, then it's actually cyclic, and the Galois group is actually canonically isomorphic to the E torsion of K star. Now, the proof says that this follows from the isomorphism of OT KL with the E torsion of K star. For L over K to be Galois, the cardinality of the group of automorphisms, the group of K automorphisms of L, should be equal to its degree. But the group of K automorphisms, this is isomorphic to this. So it's the same as saying that the cardinality of this group should be equal to E. And that is equal to E. I mean, what is the cardinality of this group? Normally, it's equal to the GCD of QK minus 1 and E. So this is equal to E precisely when, of course, E divides QK minus 1, which is the same as saying that QK is congruent to 1 modulo E. And whether this holds or not, this group is always cyclic. So when this holds, the extension is not only Galois, but it's actually cyclic, because the group is cyclic, because this group is cyclic. Okay. The next proposition says that suppose we have a P field K. This is a finite extension. And then I have another extension. Let's take it to be finite as well. And then I can take the compositum of L and K prime. I call it LK prime. Basically, that LK prime, this compositum, is the smallest field containing both L and K prime. The proposition is that if L over K is tame, then this compositum is also tame, but over K prime, of course. It cannot possibly be tame in general over K, because this might be wild, possibly, which means that the ramification index here might be divisible by P, and then there is no way that the ramification index of LK prime over K will be prime to P. Because it's the product of this ramification index and this ramification index. If one of the factors is divisible by P, then the product is divisible by P. There's no way the product can be prime to P. But Over K prime, it is tame. That is this is tame if this is tame, and that's the proposition. Okay, let's prove this. So it says, let's first take the maximal unramified extension of K in L. We have discussed this, right? You take the compositum of all unramified extensions of K inside L, and that is a certain extension, L naught, which is unramified over K, and such that L is totally ramified over L naught. Fine. So that's by definition L naught, and let's take E to be the degree of L over L naught. So that's also the ramification index of L over L naught. And since L is totally ramified over L naught of degree E, I can write it as L naught adjoined Eth root of pi for some uniformizer pi of L naught. Okay, but I already know that if I take the compositum of this unramified extension L naught and K prime, then the result is unramified over K prime. It's not very difficult to see either, because this L naught is, after all, the splitting field of some polynomial of the form t to the q to the f minus t, something like that. And the splitting field of every such polynomial is unramified. And conversely, every unramified extension of degree f is the splitting field of this polynomial. So when I take the compositum of L naught and K prime, I'll get the splitting field of this polynomial over K prime, and therefore it will continue to be unramified, which is to say that L naught K prime is unramified over K prime. So it's enough to show that when I adjoin an Eth root of pi to this L naught K prime, of course, I'll get L K prime in that case. It's enough to show that this is totally ramified over L naught K prime. Okay, so this follows from the following observation. It says that whenever I have a P field M, I have an integer which is prime to P, and I have some invertible element, some non-zero beta in M star, and I join an Eth root of that beta to get some extension N of M. M alpha. Alpha is an Eth root of beta, and beta is invertible in M. It's non-zero element of M. The important thing is that E is prime to P. And the lemma says that in such a situation, this N is separable over M, and it's tamely ramified. Okay, so this proof I'm going to omit. You can sort of treat it as an exercise. It's not very difficult, right? So now, so this it will imply that now you're just adjoining an Eth root of pi. This pi need not be pi is a uniformizer of, what was it, a uniformizer? It was a uniformizer of L naught. But it need not be a uniformizer of L naught K prime. Okay. But of course, it remains a non-zero element, and you are joining an Eth root of a non-zero element, which will give you a tamely ramified extension, because this E is prime to P. Okay. So the next proposition says that if I have two finite separable is assumed all my extensions are going to be separable. So if I have two tamely ramified extensions of K, then so is their compositum. I take their compositum and that continues to be tamely ramified over K. So that, of course, follows from what we have just seen. So you have L, no, this is called K, it's not L. So you have, what is it, K here, and you take L1, take L2, and the previous proposition says that this is tame by the previous proposition, and this is tame by hypothesis. So this is tame by transitivity of tameness, which is something we have already proved. Okay. So now we can say that an algebraic extension of finite or infinite degree is going to be called tamely ramified if all finite subextensions are tamely ramified. Okay. And these things which we have proved, this proposition and the previous proposition here, they imply that if I fix a separable algebraic closure of my P field K, then I take the compositum of all finite tamely ramified extensions, then that extension is going to be a tamely ramified extension of K. And it's called the maximal tamely ramified extension of K. Okay. So just as you have, let's put it this way, you have K here, and let's call K sep the separable algebraic closure of K. Then inside this you have something which might be called K tame, which is the maximal tamely ramified extension of K in K tame, in K sep, and then you have KNR, or this is the maximal unramified extension of K in K sep. Okay. So now, what is this proposition? What it says is that if I have a P field K, right, this is a P field, which means it's complete for a discrete valuation with finite residue field. And I have a tame extension of degree E, or of ramification index E, not degree. The degree could be anything. The ramification index is what counts. If I have a tame extension of ramification index E, and I have another extension M, whose ramification index is a multiple of E. It's D times E for some D, which is positive. Okay. Then the assertion is that the compositum LM, which is going to be here somewhere, right? LM. This compositum is actually unramified over M. What our previous propositions will tell you is that, oh, this is tame and this is tame. So this LM is going to be tame over K. It's going to be tame over M and also over K, because this is tame and this is tame. But this proposition is saying something new, which is saying that LM is actually going to be unramified. This is unramified over M. It cannot possibly be unramified over K, right? Because the ramification index is divisible by E, and it's actually divisible by d times E. But Lm is unramified over M is what the proposition says. So L over K is tame. Let's take the maximal unramified extension L naught of K in L. Okay, so L is going to be L naught adjoin an Eth root of pi, where pi is some uniformizer of L naught. Oh goodness. Okay, right. So let me do without my pencil for some time. Is that going to be? So let me use this screen, or while I think about what to use, whether to use this screen or that screen, let me ask. Okay, so there seem to be no questions. So let me continue. Let me take the maximal unramified extension L naught of K in L, and then L is obtained from L naught by adjoining the Eth root of some uniformizer of L naught. Now, let's just look at ML naught first. I have to say something about ML, M and ML. This is what I have to say something about. But let me first say something about ML naught. That is certainly going to be unramified over M. Why is that? That's because the ramification index here is 1. By definition, no? L naught is unramified over K. The ramification index here is DE. What's the ramification index here? So this says that the ramification index here is also DE. Okay, so one way to see it is to go. So to start with a uniformizer here, pi k, then it will remain a uniformizer here, pi k. Here it will become pi m to the power dE, right? And so this no, I don't need to prove this, because we have already seen that when I take the composite term with an unramified extension, I get an unramified extension, okay? So this is not what I need to prove. This, we have already proved that this is unramified. What I conclude from this is that the ramification index here is equal to DE, because the ramification index going this way is 1 times something which I don't know. Going this way is DE times 1. This product has to be equal to this product. So this has to be equal to DE. And that is what this assertion, this diagram is showing, that the ramification index of ML naught over L naught is DE. Okay. Now I take a uniformizer of ML naught and I write my pi as alpha times omega to the power dE. dE is the ramification index, and alpha is some unit of L naught. But this E is prime to P. So when I adjoin an Eth root of alpha, I'll get an unramified extension. This we have already seen, right? If I have a P field K, I have an alpha which is in OK star, and I have an E which is prime to P, then K Eth root of alpha is unramified. This we have seen. So that is what is being said. This is what is being said here. I have ML naught, I join an Eth root of alpha, but this E is prime to P and alpha is unit. Therefore, it's unramified. Fine. But inside this, I have this pi to the power d times Eth root of alpha. The Eth power of this is equal to pi. So it contains an Eth root of this pi. Okay. And in other words, this ML is contained in this unramified extension of ML naught. ML is unramified over ML naught because it's contained in this unramified extension. Okay. So it's unramified over M as well because ML naught over M is also unramified, right? So this is something which is sometimes called Abhyankar's lemma, or similar things are called, which one? Where is it? Yeah. Yeah, this proposition is sometimes called Abhyankar's lemma. It's a way of killing ramification. This one was ramified, and this is also ramified, but the ramification index is a multiple of the ramification index here. Then the compositum becomes unramified over M. That's Abhyankar's lemma, and that was a proof. Okay, so we have been discussing these totally ramified extensions. So there's something in the chat box. Yeah. Okay, so we have been discussing totally ramified extensions of degree prime to P. But now let's look at extensions which have ramification index E prime to P, but which also have some residual degree F. The residual degree, we allow it to be some integer other than 1. For totally ramified extensions, the residual degree is 1. Now we take F to be an arbitrary integer. So then let us set up some notation. Let's denote by Kf the unramified extension of degree F over K. We know that it's cyclic, right? So the Galois group I'll denote by GF. It's the Galois group of Kf over K. And the problem is that given an integer which is prime to P, I want to understand when two extensions of Kf, these are both totally ramified of degree E over Kf. So the question is, it may happen that they are not Kf isomorphic, but when is it that they are K isomorphic? To ask for things to be K isomorphic is to not ask as much as asking for them to be Kf isomorphic, right? Because if they are Kf isomorphic, then of course they are going to be K isomorphic, but the converse need not be true. Let me give some stupid example. Let's see. I mean, I don't know. You have C and that's not a good example, but anyway, we'll see in our, we'll soon come to examples. So the problem should be clear. You see, basically I've got two extensions of KF, and I want to find out when they are isomorphic over K. They may not be isomorphic over KF, but when are they isomorphic over K is the question. Okay. So let's write our, the two extensions are what? Adjoining an eth root of pi and an eth root of pi star, pi prime, where both pi and pi prime are uniformizers of K, right? That was the notation. So since they are uniformizers of K, both pi and pi prime, I can write them as u times pi k and u prime times pi k, where I have fixed some uniformizer of K. Of course, this uniformizer of K is also going to be a uniformizer of Kf, right? Because Kf is unramified over K, right? And the proposition says that this L is going to be isomorphic to L prime, K isomorphic to L prime, if and only if the images of these two units, U bar and U prime bar, in the units modulo eth powers, units of Kf modulo eth powers, these images are in the same GF orbit. This GF is a group which acts on this, right? Why does GF act on this? Because GF actually acts on KF, on KF, OF, or rather OKF. It acts on KF star, it acts on OKF star, and finally what we want is that it acts on OKF star modulo eth powers. GF acts on this, right? It acts on this, and if these units have the same image in the, not the same image, then the same GF orbit, they might have different images in this group, but these should be they should differ by some element of the Galois group. They should be Galois conjugates in this sense. So that's the proposition, and here's the proof. So suppose that, so being in the same orbit means that sigma, that there's some sigma in GF such that sigma of u is equal to epsilon to the power e times u prime. That's what it means for them to be, for their images to be in the same GF orbit. Okay. Then I define sigma tilde from KF, from this polynomial ring to the same polynomial ring, and it's just it's an automorphism of rings, right? Which will take every A in KF, every coefficient, to sigma of A, because sigma is after all an automorphism of KF over K, right? So every A in KF, sigma A makes sense. The important thing is, what does it take T to? It takes T to itself. Under this automorphism, what will U be taken to? It'll be taken to sigma of U, of course, because U is in here. U is or rather it's here, up here. U should be, okay, so it should have been mentioned here that U and U prime, pi k is a fixed uniformizer, but U and U prime are in OK F star, right? Yeah. Okay, so it takes U to sigma of U. So this is the sigma prime which I have just defined. From here, I have this arrow downwards to L prime, right? Which takes my T to eth root of pi prime. That is the extension L prime of Kf. Now, when I compose them, I'll get this map from Kft to L prime, and it takes, when I look at this element here in L prime, I find that it is equal to sigma u of pi k. In other words, I mean, see, this is the map which I've defined. This is the usual map of the quotient map. Then I get the composite, and I have the quotient map here as well. The point is that there's a unique map here making this diagram commute. That's what we have verified. Okay, so you get a homomorphism like this horizontal one here. It's a homomorphism of fields, so it's injective, but L and L prime have the same dimension over K, so it's actually an isomorphism of K vector spaces, and because it's a homomorphism of fields, it's an isomorphism of fields as well. Okay, so the converse is also something similar. It's not terribly exciting to go through it, I believe that it's not very difficult to just read what is written here. But okay, let me go through it. So conversely, suppose we are given an K isomorphism. I don't know why it's called sigma tilde. Whatever it is. Let's continue to call it sigma tilde. Suppose I'm given a K isomorphism like this. Then sigma tilde of Kf, what is it going to be? It has to be Kf, because Kf is the maximal unramified extension of K in L as well as L prime. Because L as well as L prime are totally ramified over Kf. So sigma prime will take Kf to Kf. Fine. So, and let's define sigma to be the restriction of sigma prime to Kf. So that is an element of the Galois group of Kf over K. Now, what does sigma prime take this eth root to? Because this u prime is epsilon to the power e times u, it'll take it to, we get this. No, then that's what we have to prove. This is what we have to prove, but okay. So in any case, sigma tilde of this has to be epsilon times this, because this is a uniformizer of L prime and this is a uniformizer of L, exactly. So I get some epsilon which is in O L prime star. Now let's raise this equation here. Let's raise it to the power E. Let's raise it to the power E. Then I'll get sigma tilde of u pi k is equal to epsilon to the power E times u prime pi k. I can cancel. Pi k is actually in k, so it's in, I can cancel it from both sides, and I'll get sigma of u is equal to epsilon to the power E times u prime. So sigma epsilon to the power E belongs to Kf. But this Kf, when I adjoin epsilon to it, its eth power belongs to kf, right? That's what we have seen here. But this extension is therefore going to be unramified. Whereas L is totally ramified over kf. This is unramified and this is totally ramified. That means that epsilon has to be actually, I mean, this extension actually has to be kf, epsilon has to be equal to kf. Okay, so that's how you prove that u and u prime differ by the eth power of some unit in kf. Okay, so let's get back to our notation. K is a P field. P is of course a prime number. Pi is a uniformizer of K. E and F are integers which are positive, and E is prime to P. Okay. What have we, so this maybe is a kind of summary. We have seen that every extension L of K of residual degree F and ramification index E is of the form Kf adjoin eth root of some u times alpha, u times pi, for some u in OK star, OKF star, some unit of Kf. Now, in terms of this, can we say when this extension L is going to be Galois over K? Huh? This sort of gives you all extensions of ramification index E and residual degree F. They can all be written like this. That's what we have proved. And in terms of this, this way of writing L, can we say when L is going to be Galois over K? And the proposition says that it's Galois over K precisely when Kf to the power Qk to the power F is congruent to 1 modulo E. That's the first condition. And U to the power K Qk minus 1 is congruent to 1 modulo Pk. Okay, so there are these two conditions on U and I mean maybe just one condition on U. The other condition is on the on Qkf. It should be congruent to 1 modulo E. In other words, E must divide Qkf minus 1. Okay, so let's prove this. So for what is required for L over K to be Galois? It contains an intermediate extension which is Kf, right? So a necessary condition for L to be Galois over K is that L should be Galois over Kf. And over Kf, it's totally ramified. And we have already seen when a totally but tamely ramified extension is Galois over the base field. And that condition was that E, the ramification index, should divide the order of the multiplicative group of the residue field. The residue field here has cardinality Qk to the power F. The multiplicative group has cardinality Qk to the power F minus 1, and it should be divisible by E. That is a necessary condition for K to be L to be Galois over K. That it should be Galois over Kf. Now suppose this condition is satisfied. And then we take an element phi in the Galois group of, not an element, the element phi, which I'm going to call phi. It is the canonical generator of this extension. Kf over K, remember, is not this unramified extension of degree F is not only cyclic, but the Galois group has a canonical generator, which maps to the Frobenius at the level of the residue fields. The Frobenius is raising to the power Q sub K because the residue field of K has cardinality Q sub K. Okay, so this is just to define what phi is, and the K conjugates of this U are U raised to the power QK, etc., etc. So if L is Galois over K, L is Galois over K, if and only if it contains the K conjugates of this element. And this is one of the K conjugates. It's enough for it to contain this one. Then it will contain the K conjugate of this one as well, etc. So L over K is Galois if and only if L contains this element. Now that can be seen to be equivalent to this U bar to the power K, QK minus 1 is in E'th power in this, and this is the same as saying this. Okay, so so this extension L of K of residual degree F and ramification index E is Galois over K if and only if two conditions are satisfied. First, that Qk to the power F should be congruent to 1 modulo E, and secondly, this U to the power Qk minus 1 should be congruent to 1 modulo the maximal ideal of OKF. Okay. So now what we want to do is, so we have given a criterion for it to be Galois. So the next question is, when it is Galois, what is the Galois group? Can we compute the Galois group in this case? So I'll need some notation now to compute this group. My K is my P field, and then I choose a generator of omega. Omega, remember, is the Teichmüller character, and KKF star is, of course, a multiplicative group of the residue field of KF. And I take some U, which is an rth power of this generator zeta. I mean generator because this group is cyclic of order QK to the power F minus 1, right? It's cyclic of that order. So when I take an element U, which is the rth power of zeta, this R is of course not uniquely determined. It's only determined up to, it's only determined modulo this, right? It's only determined modulo this. Just as, I mean, this, you already know this, right? So, let's also remark that if I have this congruence, then this congruence means that that E divides QK to the power F minus 1, right? So I get a map from this to this. I have my R here, and therefore it uniquely determines some element in Z mod Ez as well. Okay, that's when E divides QK to the power F minus 1. Because R is an element of this. And so this condition on U, see, remember, for it to be Galois, there were two conditions. That was just one of them, and this was the other condition. That was the first condition, and this was the second condition. So the second condition now becomes equivalent to the the whole thing, this congruence, not right. Yeah, I don't know why I did this. Okay, so So here is the computation of the Galois group of L over K when, obviously when L is Galois over K. So if L is given by adjoining an ES root of u to the power r times pi, and we suppose that it's Galois over K, then the Galois group has this presentation. It's, oh, I hope everybody knows what it means for a group to have a presentation, to give a presentation of a group in terms of generators and relations, right? Just as a cyclic group, I mean, if cyclic group of order 5 will have the presentation sigma to the 5 equals 1. That's a presentation of the cyclic group of order 5. And so I'm saying that if this is Galois over K, then the Galois group admits this presentation. It can be generated by two elements, sigma and tau. Tau has order E. Sigma, I'm not saying what its order is, but sigma to the power f, I know is tau to the power r, where this r is the same as this r. And the important thing is that the conjugation here is how sigma acts on tau by conjugation. It takes tau to the power qk. Okay, so here's a proof. Write qk minus 1 times r is equal to ne. Why can you write this? That's because of this. Qk minus 1 times r is divisible by e if it is Galois, right? So if it's divisible by e, let's write it as a multiple of e. Let's call it n times e. Then ur to the power this is going to be this, and let sigma be the extension of phi. Phi, remember, is the automorphism of kf over k, which generates the Galois group of kf over k. And let sigma be any extension of phi to L. L is, it contains a kf, right? And so every k automorphism of kf will extend to a k automorphism of L, of course. So let sigma be such an extension. What will sigma take this element to? We can, because of this relation here, you can see that it will be taken to this element. And let tau be the kf automorphism of L, which takes this element to this element. And it just remains to verify that these two, this sigma and this tau, verify that they give the presentation of the group which we have written down here. Okay. So, this is a very explicit group, and here's a little exercise. So let's take T to be the GCD of E and R, and one has to show that the order of sigma, I said the order of T, tau, is E. But the order of sigma, what is it? It's EF divided by T, where T is the GCD of E and R. Fine. So as a corollary, we get that L over K is abelian if and only if this QK is minus 1 is divisible by E. That's because if we know the presentation for a group, then we can say when that group is abelian, right? The presentation is given, and it's going to be a commutative group if and only if tau to the power qk is equal to tau, because sigma tau sigma inverse is tau to the power qk. That was one of the relations in the presentation. So for it to be commutative, sigma tau should be equal to tau sigma, right? Or rather, sigma tau, sigma inverse should be equal to tau. So this tau should be equal to this. That's what is being said, which is equal to this, right? But the order of tau is e. So if the order of tau is e, and if you want tau to the power qk minus 1 to be equal to 1, then this qk minus 1 better be a multiple of e. That's what we are saying, that qk minus 1 is a multiple of e. It's Abelian if and only if qk minus 1 is a multiple of e. Okay, so that finishes. This is what I would have liked to do last time, and let me come to what I would have done today if all this had been done last time. So okay, so let me summarize what we have done. Okay, so we have classified tamely ramified extensions, of our P field K of ramification index E and residual degree F. Tame, therefore, E is prime to P. Okay. And what is the classification? This is just recalling the notation. We have our field K, and QK is the cardinality of the residue field. This is cardinality of KK. And similarly, QK to the power F is the cardinality of the residue field of KF. This KF over K is Galois, and GF is the Galois group. So it acts on various things, including this KKF star modulo KKF star to the power E. And the orbits for the GF action on this group, GF acts on this group, and therefore you have orbits under this action. These orbits correspond to K isomorphism classes of extensions of K of residual degree F and ramification index E. Of course, you up to K isomorphism, right? So these two sets are in bijection, but I don't have a canonical bijection. You get a bijection when you fix a uniformizer pi K of K. Once you have fixed the isomorphism, you send the GF orbit of U bar. U is an element of K, K, F star, right? You send the U, and what is U bar? U bar is, of course, its image in K, K, F star modulo K, K, F star to the power E. So you send the GK orbit of U bar. It's not even U bar, which is, it's the GF orbit of U bar, which matters, and you send it to KF adjoint Eth root of U times pi K. See, I've fixed an uniformizer pi K, and then I get term. So this I'll just abbreviate it to L sub U, no? This KF Eth root of U pi K, I'll just abbreviate it as LU. Okay, so when is LU? Galois over K. We have seen this already. I mean, this is a summary. I'm recalling what we have done. So there were two conditions. That this was the first condition this year, and this was the second condition. So the second condition can be, this condition can be interpreted as saying that the GF orbit of U bar is just reduced to U bar itself. Or it can also be viewed as saying that U bar is actually in KK star modulo KK star to the power E, which is a subgroup of KKF star modulo KKF star to the power E. See, U bar is normally in this, and this condition here says that U bar should be in this subgroup. Okay, and recall that LU is Galois over K if and only if QK minus 1 is divisible by E. So here is what can be called an unexpected consequence of this. It says that if one such extension, what do you mean such extension? One extension of residual degree F and ramification index E, if one such extension is abelian over K, then every such extension is abelian over K. Okay, that's because it's just a question of whether QK is divisible by QK minus 1 is divisible by E or not. Okay, and that's independent of what F is and I mean what that particular extension is. What F is, what U is, etc. Right? Okay, so we have discussed when LU is abelian over K. When is it cyclic? When is it cyclic? Okay, that's an exercise which you might want to try your hand at. And here's a hint: you take a generator of this multiplicative group. You write your U as the rth power of this generator, and then R is uniquely determined modulo this QK to the power F minus 1. And it has this presentation, right? So now you have to check here, this is the presentation because we are looking at the abelian case. For it to be cyclic, of course, it has to be abelian before it can be cyclic. So now it has this presentation. So the question reduces to a question group theory. You are given a group with two generators, tau and sigma. Tau has order E, sigma to the F is tau to the R, and tau and sigma commute. When is this group cyclic? R, of course, is uniquely determined modulo this. So you can try to do this exercise to find out when it is cyclic. And here is something which I get as a corollary, that if I take all totally ramified abelian extensions of K, all totally ramified abelian extensions, so the residual degree is equal to 1, but the ramification index can be arbitrary. The condition, subject to the condition that it's abelian over K. And the corollary says that this compositum is actually just obtained from K by adjoining the QK minus 1th roots of everything in K star. Adjoin the QK minus 1th roots of every X in K star. That's just a corollary of what we have just seen. Because being a abelian is equivalent to QK minus 1, or QK is congruent to 1 modulo E, right? Okay, so let's get back to the same notation. We have our P field K. We have an integer E, which is prime to P, and an integer F. And we have the set of finite extensions of K of ramification index E and residual degree F up to K isomorphism. But how many such extensions are there? How many of them are Galois over K? How many of them are abelian over K? We should be able to answer these questions if we have because we have a parameterization of this set. this set, I'm soon going to call it maybe TEF or something. The notation, yeah, here it is. TEF is the set of all finite extensions of K of ramification index E, residual degree F up to K isomorphism. Excuse me. Right? Yeah, okay, so why don't you take a look at this notation and ask me any questions if you have any. Let's wait for 1 minute for questions. Okay, so the notation, I'll just write a little q for qk. Maybe I should have done it earlier. I'll abbreviate the GCD of E and qk, q to the f minus 1. This GCD, I'll call it just G. Remember, this is the order of the group, what was it? K, F star modulo K, F star to the power E. It's the order of this group, this G. For every divisor T of G, I'll write chi Q of T for the order of Q bar. Q is fixed, right? The order of Q bar in Z mod TZ star. Why is Q bar invertible in modulo T? That's because Q is invertible, of course, modulo this, no? Modulo this, it's invertible because Q is prime to, Q is prime to, of course, Q to the F minus 1. So it's invertible here, and therefore it's invertible modulo G, and therefore it's invertible modulo T, because these groups are all quotients of this big group in which Q bar is invertible. Moreover, this chi Qt divides phi of T. Phi of T is the order of this group, and this is the order of this element of the group. So of course, the order of an element divides the order of the group, and that's what is being said here. Okay, so I need this notation in order to express this is the cardinality, the number of, not totally, but the number of extensions of K of ramification index E and residual degree F up to K isomorphism. This number is equal to this sum. Is the sum of over all divisors of G of phi T, which is the order of the group Z mod TZ star, divided by this, which is the order of Q bar in this group. Okay, so that is what we have to prove. And the proposition continues. If G is equal to E, G, remember, was the GCD of Q to the F minus 1, and E, if G is equal to E, it's the same as saying that Q divides, Q to the F is equal to 1 modulo E, meaning E divides Q to the F minus 1. Then G1, which is by definition the GCD of E and Q minus 1, of these extensions are Galois over K. Remember, we wanted to see how many extensions are there, how many of them are Galois, how many of them are abelian, and then this is what we are now computing. We are saying the total number of extensions is this sum here. this sum, this sum here. And if G is equal to E, then these many are Galois. If G1 is equal to E, G1 is this here, then every L is a billion over K. This we already seen. If one of them is a billion, then all of them are billion. So that's okay. So how do we prove such a thing? Basically, I mean, it's just a matter of counting, because we have this parametrization, and then the parametrization is that this TEF is basically in bijection with, what was it, KKF star modulo KKF star to the power. It's basically this bijection which allows you to compute the cardinality of this. And this we know what the cardinality of this. No, excuse me. It's not this. Or what we have, it's TEF is in bijection with GF orbits in KKF star modulo KKF star to the power E. The GF orbits, not this itself, but GF acts on this. GF is a Galois group. It acts on this, and the orbits are in bijection with this set. So, in order to compute the number of orbits, I mean, this group is cyclic of some order. I mean, it's cyclic of order G. That's what it has been called. So let G be any integer, and let capital G be a cyclic group of order little g, and let Q be any integer which is invertible modulo G. Then, in such a situation, I can make the group Z act on the little group G by sending the element 1 to the automorphism which takes every x to the power Q. That's an automorphism, right? Because Q is invertible in this. Wait a minute. It's not, I mean, yeah, okay. Right. So, right. And the point is, so this is an action of the group Z on this group G, and the point of the lemma is that the number of orbits for this action is exactly the sum. And that, in fact, basically is a small exercise which you people are all invited to try your hand at. It's not very difficult. Just have to think a little bit. It's pure algebra, right? And it's dealing with small things. Just a cyclic group of order, some cyclic group, and some invertible element in that group, and then you get this action of Z, and how many orbits are there? You should try it. Okay. Then we have to see how many of them are Galois. So that this lemma will give you that this is the number of elements in TEF, tamely ramified extensions of K, of ramification index E, and residual degree F. That gives you the number of such things, right? But how many of them are Galois? So we had seen that this is some LU, where U is in this, is Galois if and only if G is equal to E, and this belongs to KK star as a subgroup of KKF star modulo KKF star to the power. This is the subgroup, and U normally belongs to this. If it happens to belong to this subgroup and G is equal to E, then L U over K is gamma. Okay, yeah, so all this is written out here. What is U bar? It's the image. What is what's the order of this? It's G1, right? So the action, what is the action of GF on this? It's trivial, because GF is the Galois group, so GF acts trivially on K, on OK, on KK, on KK star, and on KK star modulo KK star to the power E. Acts trivially on all these groups. So if it acts trivially on this, the number of orbits is equal to the cardinal of this, and the cardinal or the order of this group, and the order is G1, of course. It's the GCD of E and Q minus 1, because this group is cyclic of order Q minus 1. The order of the group K star is equal to Q minus 1. So the order of the group KK star modulo KK star to the power E is the GCD of E and Q minus 1. And we've been calling this number G1. That's it. Okay. So if G is equal to E, then G1 of these L are Galois over K. And that proves what we wanted, right? So you see, this is beautiful, and this is sort of very elementary and easy, because we are looking at tamely ramified extensions. So once we come to wildly ramified extensions, those where the ramification index is divisible by the residual characteristic P, then things will get much more complicated. And there's no such simple classification of wildly ramified extensions. So wildly ramified extensions are more difficult. So let me just end with this, that they are more difficult to classify. Okay. Are there any questions? Yeah. So it's good that the internet did not disrupt the class today. And next time, of course, we'll start a new topic, because this one is over. Tamely ramified extensions and their classification, parametrization, which ones are Galois, which ones are abelian. So this part is over. Now we'll get into other things. I'm not sure what it's going to be. Maybe the discriminant and the different, maybe the ramification filtration. We'll see. Okay. So are there any questions? Yeah. Well, if not, I'll end this session and see you next week, or in fact on Friday first for the tutorial. Okay then.